Alright, time for another draftphysics.com video presentation. Continuing the format of using the Wikipedia pages as a way to itemize and categorize the different subjects in physics. And so I think it's working out perfectly fine, both demonstrating that, the classical popular physics is way under evidenced and it's just a bunch of storytelling, and that there are better stories, frankly, that can be told regarding the truth and such. So space is it's really such, it's such an important conceptual idea, but there's no physics in the space itself, the idea of space, okay, without the matter and without the force, just the idea of some expanse that is basically positions, and that's how Newton saw it. Space was about positions. It's just about here's a place and here's a place, and then stuff happens, and those places don't move. So something can move and then be in this place, and then it can move out of this place, but it wasn't this little piece of space. And so it's not a substance. It's not a thing. It's just a consequence of stuff having an arena to move in, and that's it. And the arena has places. There's molecules of air in the Superdome or something. I guess they tore that down, didn't they? After everybody pooed in it. But anyway, I don't know if they replaced it with something. I don't know. A sign saying never again. Anyway, all right, so it's a really important concept, and it does get into the whole Newton-Leibniz controversy, because basically this is sort of the argument. Either you believe in this idea that space is this expanse into which there are the substance of the stuff happening, where there's this stuff called force that has energy, and then there's this stuff called matter that gets pushed around by the energy. And when the matter gets pushed around or moved by the energy, the field of energy changes because it reflects off the matter different. Very simple concept. No, the idea of relativity, of course, exists because there's two relative perspectives. If I have something, I have a point A and a point B, and something moves this way. Well, from point B's perspective or point A's perspective, they can say it did a different thing because it did a different thing relative to them. All right, but the fact is it's an absolute thing, and they can describe the absolute. So there is an absolute space that has in it relative positions. Okay. Space is a three-dimensional. See, they shouldn't tell us what it is. They should tell us what they say. Okay, we say space is. So we, the editors of Wikipedia, say space is a three-dimensional continuum containing positions and directions. Now, isn't that interesting? So that's the classical non-relativistic in any modern sense of the word relativity. In the modern sense of the word relativity, there is no absolute space, and there's just relative relationships. In classical physics, physical space is often conceived in three linear dimensions. Well, you just described it as that. Okay. So this image over here, three basic dimensions, which really create six sub-dimensions, you could argue. But anyway, left, right, up, down, forward, back. All right. Modern physics usually consider it with time. So, again, which doesn't make any sense, frankly. It doesn't, dimensional time. No, there's no dimensional time. There's just time, period. To be part of a boundless four-dimensional continuum known as space-time. So, again, that's what they consider it. That's what you've decided is the truth, and it just screws up all rational physics. Just throw rational physics out the window, because now you've created a fake universe where force doesn't matter and position doesn't matter. I mean, the forces obviously can't be a consistent thing if you're saying the frames change when or how you're going to hit by the force, when the only thing that decides is the speed of light, and you're breaking that. with your relativity. The concept of space is considered to be of fundamental importance to an understanding of the physical universe. So that's a good sentence in the sense that, yes, this really is important. And the fact is, you fucked it, okay? You broke it, you ruined it. Galileo, Descartes, Newton kind of set you up to get right answers for the rest of your life, and you decided to say, screw it, let's be morons. 1 + 1 = 4. However, disagreement continues between philosophers. What does philosophers have to do with it? It's physics. It's not philosophers. Over whether it is itself an entity. Well, yeah, of course it can't be, because it doesn't do anything. It can't be an entity because it doesn't do anything. So that's the whole point. Yes, if you're a relativist and you believe in warped space-time, well, then it has to be a substance, as Einstein conceded. Well, if it's making stuff move, then it's got to be a substance. It can't be a nothing. Only a something can make things move. So if you're saying a bending of space causes something, well, then that space must be real. It must be a substance. A relationship between entities are part of a conceptual framework. It doesn't. There's no conceptual framework between the simple idea that there are just these positions in space. That here is different than here, is different than here, and 1 billion light years from here, it's the same truth. They're just positions in space, and you can't break them. In the 19th and 20th centuries, mathematicians, so with philosophers and mathematicians, they shouldn't really have anything to do with physics, anyway, began to examine geometries that are non-Euclidean, so adding a 4th dimension or a 5th dimension or a 6th dimension, which don't fit because it can't create the right angles. This 3-dimensional thing works because it's all right angles, 90-degree angles. You can't make a 4th dimension that's 90 degrees to the other 3 dimensions, so there isn't any such thing. Anyway, in which space is conceived as curved rather than flat. Curved how? Curved what? You mean the flat parts are curved also? It's just too silly. As in the Euclidean space. So they just got rid of the idea of straight lines and decided everything's a crooked line. According to Albert Einstein's theory of general relativity, I don't even know if the theory actually says any of this crap, frankly. Space around gravitational fields isn't supposed to be just space around a gravitational body that is a mass. So it's about space around a mass, not a field. Deviates from Euclidean space. Experimental tests of general relativity have confirmed, so this is the lie part, always thrown in, that there's a bunch of great experiments that prove that space is bent. No, there really aren't. There's these little detailed, complex experiments that have stuff to do with breaking clocks. It doesn't have anything to do with proving, relativity. Have confirmed that non-Euclidean geometries provide a better model for the shape of space. So that's just nonsense. That it's a better model, that these tests prove it's a better model, or any of that crap has ever happened. So that's just nonsense. All right. They don't have any experiments. All right. Debates concerning the nature, essence of the mode of existence of space date back to antiquity, namely the treatise like, Timaeus of Plato. Who cares about all this crap? Socrates, of course. So blah, blah. Who cares about the origin of the word? Primarily matter, space. Who cares? Let's see. Other philosophers, notably Gottfried Leibniz, von Leibniz, he liked to be called von Leibniz, thought instead that space was in fact a collection of relationships between objects. So again, what can that even mean? Relationships between objects in what? How can they have a relationship unless they're spatially different from each other? So this is where we get into some sort of ether soul or something. Somehow things aren't separate. It's just too ridiculous. Given by their distance and direction from one another. Right. And How does that change magically? I mean, all the evidence points to the fact that none of that changes magically. That you have to apply a speed of light force. You can't even see something until the light gets to you. I mean, it's so obviously got all kinds of physical limitations. All right. In the 18th century, the philosopher and theologian George Berkeley, who cares, attempted to refute the visibility of spectral depth. What the fuck is that? Visibility of spectral depth. In the essay towards the new theory of vision. Well, fuck you. Later, what is this? The metaphysician Immanuel Kant. And I mean, these are people that don't have any qualifications to making physics arguments. Said that the concept of space and time are not empirical ones, derived from experiences of the outside world. So these are just people who think it's mind over matter. That somehow if we believe in, gingerbread houses, then they'll poof into existence. They are elements of an already given systematic framework that humans possess and use to structure all experiences. So this is just such babble. I can't believe they threw this babble in. Kant referred to the experience of space in his critique of pure reason as being a subjective pure a priori from intuition. So what's the point of talking about space being subjective? I mean, every experimental device sees exactly what we see in a sense of the space being real. The speed of light being tested over and over again. The speed of force. Okay, I should learn how to say that every time. The speed of force is so reliable. The fact of the dimensions of space is so reliable. Galaxies don't pop in and out of existence. I mean, it's just silly. So they just included this big pile of fable and nonsense. All right, Galileo. Galilean and Cartesian theories about space, matter, and motion are at the foundation of the scientific revolution. Yet, unfortunately, we threw it all away to, jump on a woo wagon, which is understood to have culminated with the publication of Newton's Principia de Mathematica in 1687. Newton's theories about space and time helped him explain the movement of objects. Newton's conclusion, that it has every appearance, that every fact seems to indicate that this is how the universe works, that there's force and matter in space, and that the space is absolute. And that's why he started the book with this exact argument. The beginning of his book is basically first telling you there is this stuff called space, and these are absolute positions in space, and everything happens by moving from closer or further away from these positions. Newton's theory about space and time, while his theories of space is considered the most influential in physics, it emerged from his predecessors' ideas about the same. There's a point where it's just kind of bullshit to say that somebody, that any improvement you make to something is just a version of somebody else's. And there's what's the point of saying that every time? As one of the pioneers of modern science, Galileo revised and as the established Aristotelian and Plotomatic ideas about geocentric cosmos. So now they're just going to argue about, okay, so what? They got the Sun-Earth relationship wrong, and then they finally figured out, oh yeah, stuff isn't revolving around the Earth. We're not the center of the universe. The universe is much bigger than we thought, blah, 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 blah. All right, he backed the Copernican theory that the universe is heliocentric with a stationary sun at the center of the planets, right? And he couldn't know how stationary the sun actually is, and we still don't. We didn't even figure out till like 5 years ago that the sun might be rotating. Okay, I don't know how long ago they started talking about that, but I'm just saying, the sun is a little bit complicated to see into because it's really big and really far away. including the Earth. Okay, revolving around the sun. If the Earth moved, the Aristotelian belief that its natural tendency was to remain at rest was in question. So this is this isn't really the big idea stuff. Galileo wanted to prove instead that the sun moved around its axis. So this really isn't talking about Galileo as a person who believed in relativity, but it was incidental relativity. There wasn't absolute space. The motion was as natural to an object as the state of rest. In other words, for Galileo, celestial bodies, including the Earth, were naturally inclined to move in circles. This view displaced other Aristotelian idea that all objects gravitated towards their designated natural place of belonging. So, I mean, yeah, okay, the stuff that he fixed that was really, really broken versus the more interesting stuff where he found the subtleties of the idea that stuff, yeah, everything, what falls down, what goes up must come down, and he did something more than that. Okay, he quantified that function. All right, and then Descartes. Let's see what they'll paraphrase Descartes into a simpleton too, I guess. Descartes set out to replace the Aristotelian worldview with a theory about space and motion as determined by natural laws. They're all determining it by laws, rules, so this is more nonsense. In other words, he sought a metaphysical foundation. No, he didn't. Or a mechanical explanation. Isn't that just so funny that they call mechanical metaphysical? He sought his point is that it's a machine. It is a clock, and it's ticking. And every tick, it does a certain thing, and everything stays in the system, and there's not more bits coming in, and there's not more anything happening. It's a machine God made, and he pushed it, and that's the end of it. That was Descartes' statement, essentially, is that it's a self-sustaining system. The energy never dies. Okay, explanation for his theories about matter and motion. Cartesian space was Euclidean in structure. So, I mean, this is just so, nonsense. Infinite. Who cares about this infinite word? All right, nobody had any evidence to confirm or deny that one. Uniform is the key word, and this idea of flat is, well, of course, it's straight lines, yes. It was defined as that which contained matter. Conversely, matter by definition had a, whatever this is, this spectral extension. What is that even? What with this extension shit? There's no extension. There's the matter, okay? It doesn't have anything else. And there's force in the universe, and the force, like light bouncing off of me. I don't have any extension. I don't have photons. The photons have to hit me and then bounce off of me. So that there was no such thing as empty space. Right, so the fact that he thought it was some sort of goop, okay, and that the goop transferred energy is sort of incidental to the fact that he thought the positions in space were real. That's the key point. The Cartesian notion of space was closely linked to his theories about the notion of a body, mind, and matter. He is famously known for his cognito sum or whatever. I think, therefore I am. As a simple argument, right? How do you prove your existence is, well, I just said it. I'm talking. That's proof. Lots of things are proof. Or the idea that we can only be certain of the fact that we can doubt and therefore think and therefore exist. So that's your interpretation of what he's saying. I think it's kind of obvious he's saying it's kind of without question that I'm here because I'm here. Yeah, we couldn't have this conversation if I wasn't here. His theories belong to the rationalist tradition, so that's a good word. Yes, let's all be rationalists, please. Which attributes knowledge about the world to our ability to think rather than to our existence. That's right, we have to think to know, okay, as the empiricists believe. Well, there's no such thing as born knowledge, so yeah, you have to acquire it all. He posited a clear distinction between the body and the mind. which I don't see the point in, but clearly there's a distinction between my foot and my brain, or my liver and my brain, or my kidneys and my brain. My brain is able to do a whole bunch of this fancy shit that the other organs aren't able to do, which is referred to as the Cartesian dualism. So there's no real dualism. Your brain is a functioning computer, and your body is a soda machine. All right. It does what the computer tells it to. All right. Following Galileo and Descartes. Okay, so yeah, this will be the Leibniz-Newton part. And this gets to this elemental understanding of whether this is a universe that can mechanically be understood or a universe of woo. All right. So, following Galileo and Descartes during the 17th century, this should say the late 1600s, to be more precise, the philosophy of space and time revolved around the ideas of Gottfried Leibniz, a German philosopher, mathematician, and Isaac Newton, who set out two opposing theories of what space is. Rather than being an entity that is independently exists over and above all matter, so that's not what Newton thought space was. He didn't think it was an entity over and above all matter, so that's sort of a lie. He just thought it was places in space. They're just positions in an empty space. Leibniz held that space is no more than a collection of spectral relations. So again, what does it mean, to say it's a relationship that isn't coherent? That somehow my relationship to this is somehow real, but that the same this doesn't have a relationship to the camera itself, and that none of these other relationships are tied to the same rules. Of course, they all have the same rules. All right, between objects in the world. Space is that which results from the places taken together. So that's perfectly consistent with Newton's argument, frankly. Unoccupied regions are those that could have objects in them. Okay, so that's again consistent with Newton. And thus spectral relations with other places. So I don't even know what that means, but clearly this is not going to be a very well drawn distinction between Leibniz and Newton. Okay. For Leibniz, then, space was an idealized abstraction. What he just described doesn't sound like an abstraction. From the relations between individual entities or their possible locations, and therefore could not be continuous. So again, how can it not be continuous if you just described it as places, but must be discrete? So who knows what they meant by that? I mean, let's see, in probability theory, well, no, that's not going to be a decent answer about discrete. Anyway, space could be thought of in a similar way to the relations between family members. Although people in the family are related to one another, the relationships do not exist independently of the people. Huh? What? Yeah, okay, you can't have frogs without tadpoles? Oh, duh. Leibniz argued that space could not exist independently of objects in the world because that implies a difference between two universes exactly alike except for the location of the material world in each universe. So it would just be silly to say that the space needs matter to be in it. That's just kind of silly, I would argue. So obviously if it has matter, fine. If it doesn't have matter, fine. It wouldn't make any difference. But since there would be no observational way of telling these universes apart, then according to the identity of indiscernibles, I mean, it's just too silly. There would be no real difference between them, except the differences. It doesn't make any sense. According to the principle of sufficient reason, some more jargon, just all this silly jargon. Any theory of space that implies that there could be these two possible universes must therefore be wrong. So I don't think Newton was speculating that there was any possibility the universe wasn't but this universe. But he certainly could speculate that the universe could have been completely different if the starting conditions were different. So again, I don't know. It's just too ridiculous, all this jargon here. Let's see. So let's see what they say about Newton, if they got this right. Newton took space to be more than relationships between material objects and based his position on observation and experimentation. His position is that there's 3 dimensions of space. Okay, that's his position. And it goes a long way that way, and a long way that way, and a long way that, there's a whole bunch of it. For a relationist, there can be no real difference between, inertial motion in which the object travels with constant velocity and non-inertial motion in which the velocity changes with time, since all spectral measurements are relative to the objects and their motions. So again, this is Newton's arguing for a rigid 3 dimensions of positions, and that everything moves relative to a place in space. You could just pick any space, any place in space. Every place in space, the universe is mechanically consistent from that position. From any position you look at it, it's mechanically the same universe. Yes, the distances will be different from your position, but the mechanical functions will be the same. It's just so... They don't need to make this that complicated. All right. But Newton argued that since non-inertial motion generates forces, it must be absolute. So I don't even know what this generate forces part is. But clearly he is arguing that space is absolute. That's the key point. That it's space itself is rigid, and the places are places, and the places don't move. This place in space, in the absolute universe, will not go anywhere. Matter will travel through it, but the space won't go anywhere. All right. He used the example of water in a spinning bucket to demonstrate his argument. So this is really bizarre. What he was demonstrating was an argument against any notion, that the universe isn't 3 rigid physical dimensions. Water in the bucket is hung from a rope and set to spin, starts with a flat surface. After a while, as the bucket continues to spin, the surface of the water becomes concave. So he used 2 examples. So a better example is having 2 objects separate as they spin. And what he's basically proving is that any spinning object basically defeats any notion of relativity, because from the edge of the spinning object you can always tell you're the one moving, because the physical event causes a change. If the universe was spinning, the water doesn't move. If the bucket's spinning, the water moves. The concave surface is therefore apparently not the result of relative motion between the bucket and the water. Instead, Newton argued it must be the result of non-inertial motion relative to space itself. Well, the real effect is that the bucket is spinning, and it's going to cause the water to spin, and they can't get around that fact. For several centuries, the bucket argument was considered decisive in showing that space must exist independently of matter. I think it's decisive in showing that any argument that there is this, the universe is the same, whether the whole universe spins or whether the bucket spins, that's the nonsense. Relativity fails. All right, so why Kant is in here, I have no idea. I mean, he's really not in any way a physicist. In the 18th century, the German philosopher Immanuel Kant developed a theory of knowledge in which knowledge is about space can be both a priori and synthetic. According to Kant, knowledge about space is synthetic. So it's just kind of silly. It's not, obviously it's not fake or unreal. And that statements about space are not simply true by virtue of the meaning of the words in the statement. Well, yeah, they are. In his words, Kant rejected the view that space must be either a substance or a relation. Instead, he came to the conclusion that space and time are not discovered by humans to be objective features of the world. So it's just, in my opinion, silly. Space as a conceptual, describable circumstance is doable, but imposed by us as part of a framework of an organizing experience. So it has nothing to do with our experience. It has to do with accurately describing what is the nature of things having two different positions. And the nature is that there's space between them, that they aren't in the same place in a area of space. Oh, I don't know. Do I want to do non-Euclidean geometry? No, I really don't. I mean, it's just silly. There isn't any bent space. There's just space, and it isn't bent. All right. I don't know if we all want to do this, all this bullshit, Gauss and Poincare. Well, let's do it. Although there was a prevailing Kantian consensus at the time, once non-Euclidean geometries had been formalized, some began to wonder whether or not physical space was curved. So again, just so silly. In my opinion, just silly. It's a silly way to describe the physical force of gravity. Carl Friedrich Gauss, a German mathematician, was the first to consider the empirical investigation of the geometrical structure of space. He thought of making a test of the sun, some of the angles of the enormous stellar triangle, and there are reports that he actually carried out a test on a small scale by triangulating mountaintops in Germany. And again, he's not going to find a crooked line anywhere. All right, and then Henri Poincare, a French mathematician and physicist of the late 19th century, introduced an important insight in which he attempted to demonstrate the futility of any attempt to discover which geometry applies to space by experiment. So again, I don't know how they could find any of this complexity. There's a straight line between the sun and the earth. There's a straight line between the earth and the moon. Straight lines work just fine. He considered the predicament that would be facing scientists if they were confined to the surface of an imaginarily large sphere with particular properties known as a sphere world. In this world, the temperature is taken to vary as much in such a way that all objects expand and contract similar propositions in different spaces on the sphere. So again, this idea that we have any need to break the straight line geometry, that somehow it doesn't work and that we need to sit there and pretend, well, what if it was a curved earth? Could we tell the difference? The very fact is that we don't tell the difference, right? It looks flat from our perspective, all right? And that's all we need to know. The curvature doesn't do anything important that affects us in any kind of real way, because from our relative position, we can't see it. We can't see the effects of curvature. With a suitable fall off in temperature, what the scientists try to measure with rods to determine the sum angles of the triangles, oh, forget it. This is such a waste of time. I just can't believe they just ruined something so simple. So that's all you really need to know, right? I mean, the subject is ruined by Einstein and all this jibber-jabber about how there's some sort of stuff called the space-time. Again, it's just another ether theory. Einstein admitted it. It's pretty much ether because it's a substance that's bendable. That's not what the universe runs on. The universe runs on force, photons. They're the things that carry all the energy, stuff like the photon is made out of. A photon is a pattern in a force, and magnetism is a pattern in a force, and gravity is a force. Is a simple way to look at it. No pattern. And that's the stuff pushing the universe together. All right. So, yeah, it's probably enough. This is really not a conversation about anything real. It's not a conversation about the real facts. And the fact is Newton's bucket experiment really hasn't been in any way debunked. It clearly does illustrate that you can see the difference between a universe spinning and the bucket spinning, because the fact is the universe isn't going to make more gravity, isn't going to make the water move, and the bucket is. All right. So, till the next time, and such and so forth and whatnot. So, yeah, I don't know how you. I mean, to me, the only way you edit this page is to point out, well, you're either a wooey kook, or you accept the three-dimensional facts. So you're either a person who does believe that there's 3 dimensions of space, that everything is in that space, and that everything is functioning based on the speed of this stuff called force. And the speed of force a billion light years from here is the same as the speed of force here, and that's why it takes so long for photons to get here. And it's a really reliable and dependable 3-dimensional universe, and it doesn't have any magical space-time in it. There's no such thing as space-time. All right. Till the next time and such. Ugh. Ugh.